Hi, my name is Reimers and I present work to you that I've done together with Niklas Penzel, Paul Bodesheim, Jakob Runge and Joachim Denzler at the Friedrich Schiller University and the German Aerospace Center in Jena. The goal of our research was to understand which features are used by a state-of-the-art automatic skin lesion classifier. Not long ago, all skin lesion classifiers looked like you can see in this picture. From the image, some predefined features were extracted, and this feature representation was used to train a shallow classifier, for example, a support vector machine, to reach a decision. However, in recent years, the state of the art has shifted more towards deep neural networks. And there's a good reason for this: performance. As was, for example, investigated by Chandel et al., deep neural networks outperform even experienced dermatologists on the HAM 10,000 dataset. These gains in performance of deep neural networks, however, also come with a drawback. This drawback is that for a deep neural network, we can no longer say which feature was extracted or which feature is used to reach a certain decision. In my opinion, understanding which feature is used by a deep neural network is critical, especially in the medical domain. And I want to give you two arguments on why I think this. And the first is the patient risks their health or well-being maybe on the prediction of a deep neural network. And since it's the well-being of the patient that is at risk, they have to be able to make the final decision. But to make an informed decision, they have to understand the reasoning behind the prediction of the deep neural network. Second, deep neural networks are actually great at extracting biases. In this picture, you can see an image from the Pascal-Vogt dataset, and it was later found out that in the Pascal-Vogt dataset, all images of horses actually contain a watermark in one of the bottom corners. And deep neural networks actually only detected the watermark to label an image as containing a horse. And especially for the medical domain, it is important that we find that this does not happen for a classifier we want to use in practice. Therefore, in this work, we want to investigate two things. First, we want to make sure that state-of-the-art skin lesion classifiers use relevant features. And as relevant features, we picked the features named in the ABCD rule that is used by dermatologists to differentiate between melanoma and nevi. Second, we also took some known biases and want to check that the state-of-the-art skin lesion classifiers do not use these biases. And to both of these, I will say more later in this talk. But before I do, I want to talk to you about how to understand which features used by a deep neural network. And the most common approach are saliency maps. The idea of saliency maps is to assign a saliency value, or relevance or importance value, to each pixel of the image. And there are three main approaches how to calculate saliency maps. One is to go off the gradient. So if a pixel has a high gradient, it is important. Second is to replace the pixel in the image and say if the output of the classifier changes a lot, if we omit this pixel or change this pixel for something else, then this pixel was important in the original decision. And third is a combination of both methods where we calculate the gradient and multiply this gradient value with the actual value in the image. However, all of these methods, or the general idea of saliency map methods, share a common drawback, and this drawback is that it only can be used for features that are directly part of the input. As an example, in this slide, I showed you the three saliency maps from before, and I want to ask you, does the network use asymmetry, the asymmetry of the lesion, or the symmetry, one of the ABCD rule features, to classify this lesion? And I would argue that from this saliency map, we cannot answer this question. Therefore, in this work, we use a different approach. The approach we use is based on the framework of causality, which was introduced by Pearl in 2009. In this framework, we can turn supervised learning into a structural causal model. And in this structural causal model, we can use Reichenbach's common cause principle to reduce the question of whether a feature is used to determine the prediction of a deep neural network down to a conditional dependence test. If you are interested in this method and want to read further, we refer you to the references in the paper. Here, we used this method to investigate two state-of-the-art skin lesion classifiers. The first classifier was introduced by Perez et al. The main idea of this classifier is test time augmentation. So instead of feeding the image directly into the neural network, we create some number of copies of this image, use different augmentations on all of these copies, feed all of these copies through the neural network, therefore get some number of classifications, and aggregate all these classifications into one final classification. We train this classifier for two binary tasks. One is the recognition of melanoma and one is the recognition of seborrheic keratosis. For each of these two tasks, we vary the number of augmentations, the backbones, and the aggregation method to get a group of 12 models for each of these tasks. The second classifier we investigate was proposed by Gesset et al. This classifier consists of an ensemble of mostly efficient nets, pre-trained on ImageNet, and also employs test time augmentation. Since this is a multi-class classifier that recognizes 8 classes, we investigated as the 8 different recognizers of the 8 different classes. However, we did not train the full ensemble. Following the code provided by Gesset et al., we trained 5 efficient nets B0 and hoped that they represent the ensemble classifier well. To investigate these classifiers, we use the following setup. We start with a test set, a set of labeled test images. For each image in the set, we extract the feature for which we want to know whether it is used by the classifiers. Then we also get the prediction from each individual classifier within a group. Now we calculate the conditional dependence between the prediction of a classifier, the feature, and the given the label. To get a result for whether this group uses a certain feature, we count how many of these tests find dependence between the prediction and the feature given the label. So here are the results of our experiments. Before we investigate the ABCD rule features and the bias features in which we are actually interested, we wanted to test the method further. Therefore, we started with a group of features which do not have any or at most very little information on the class of the skin lesion. Here we expect all the classifiers to not use these features, and the main purpose of this experiment was to demonstrate that the classifier will not have many false positives for features that are clearly not useful in classifying the skin lesion. We chose features for this group of experiments that represent the complexity of the features we want to test later. The exact features we decided on are the following. The first is the orientation of the skin lesion in the image. For this feature, we calculate the major axis of the skin lesion and compare or record the angle between this major axis and the first axis of the image. Of course, this is more a property of the image than the skin lesion, as turning the camera around will change this. Therefore, it should not have any information on the skin lesion class whatsoever. Second, we take symmetry along a random axis. While a perfectly circular skin lesion will have a high value here and a perfectly or completely asymmetric skin lesion will have a low value, we still believe that this one random axis contains little information on the skin lesion. Both of these are things we calculate from the contour of the skin lesion, similar to the symmetry and border feature we will look at later. Third, we take the image ID of the skin lesion in the ISIC archive. Since many of the biases we will look at later are also taken from the annotations in the ISIC archive, we feel like that this is a good feature to test whether annotations will lead to false positives. Note that in the ISIC archive, images are sorted by datasets, and some dataset, for example the Sonic dataset, only contain benign nevi. Therefore, the image ID might have some information on the actual classification, but we expect this information to be very little. For the final feature, we took the contour of the skin lesion and classified it using a handwritten digit recognizer trained on the MNIST dataset. Here, the skin lesion is classified as one digit starting with 0, ending with 9. This is just a complex calculation and should not have any information on the skin lesion class. The results can be found in this slide. As you can see, all of the groups use any of the features at most rarely. Since the method does not produce many false positives, we can go on to the actual interesting investigations in this work. And we start by looking at the features named in the ABCD rule. The first of these features is the symmetry. For the symmetry, we took the contour of the lesion, and here we actually took the ground truth annotation for the segmentation task in the HAM 10,000 dataset. And we check whether we can find one or two orthogonal lines to which the contour is almost symmetrical. And by almost symmetrical, we mean that the intersection over union between the original and the contour flipped along this axis is greater than 0.9. The second feature in the ABCD rule is the border feature. To calculate the border feature, we took the isoperimetric fraction, meaning we compare the area of a skin lesion to the area of a circle with the same length border. The third feature in the ABCD rule is the color feature. For this feature, we took these 6 colors named in the ABCD rule. We defined intervals for each color in the HSV color space, and then we checked for every skin lesion for how many of these 6 intervals we could find pixels that fall into this interval. Finally, we have D, the dermatological structures, and for the dermatological structures, we again rely on a ground truth annotation in a previous ISIC challenge, where for every skin lesion, the region for every dermatological structure is annotated, and therefore we can simply calculate a score of how many of these structures appear in the skin lesion. The results can be seen here. First, we find that if we compare the Paris models, the models that are trained to identify melanoma use the asymmetry and border feature, while the models that are trained to identify seborrheic keratosis do not. This is expected since the rule was developed to differentiate between melanoma and nevi and not developed to recognize seborrheic keratosis. However, we also find that the color and dermatological structure feature are used rarely or not consistently by all models. So finally, we look at known biases. The first bias we consider is the age of the patient. To find the age of the patient, we rely on the annotated metadata in the HAM 10,000 dataset. There the age is annotated up to the next 5 years. And similar for the sex of the patient, this is also annotated in the HAM 10,000 dataset and is only annotated binary as male or female. The third bias we use in this experiment is skin color. To find the skin color outside of the lesion, we extracted the top left 10 by 10 pixel corner of the image. This top left patch of the image should normally not contain the skin lesion and therefore should contain the background skin color. However, sometimes the corners of these images are black, therefore we omitted all patches that are clearly just black. Then we used PCA to reduce this 10 by 10 images or patches down to 1 dimension and ordered them by this 1 dimension. And visual inspection showed that these value of the first principal component, actually the loading of the first principal component, was a good representation of the lightness of the skin. The last bias we are looking at are colorful patches. Colorful patches exist in some of the ISIC archive images, especially in the Sonic dataset. and all images containing colorful patches also contain benign nevi. Therefore, a deep neural network might use the existence of colorful patches to classify a skin lesion as benign nevi. To check this, we use the ground or the patches annotations of Friedrich et al. And use the actual size of the colorful patch in pixels as the value of this feature. The result of this experiment can be seen here. The first observation is that the age and the colorful patches is used by the majority of classifiers in each group. In contrast, the sex of the patient is used by the majority of classifiers in no group. The only feature for which the groups show different behavior is the skin color feature. Here we see a very obvious difference between the models that recognized melanoma and the models that recognize seborrheic keratosis. To understand the reason for this bias, we plotted the distribution of skin colors for the images containing melanoma and images containing non-melanoma in the ISAC 2017 challenge dataset on which this classifier was trained. As you can see in this picture, there's no big difference between the skin colors of the images containing melanoma and containing non-melanoma. In contrast, as you can see here, there is a huge difference between the distribution of skin colors in the images containing seborrheic keratosis and containing non-seborrheic keratosis lesions. Therefore, we think that we found a bias in the 2017 challenge dataset. To summarize, in this study, we first investigated whether the method of conditional dependence can be used to understand state-of-the-art skin lesion classifiers. We found that the method does not produce many false positives, and therefore, if it produces a positive, we can trust it. Based on this, we investigated whether the state-of-the-art skin lesion classifiers use the features named in the ABCD rule, and found that some of the classifiers use some of the features. This should at least lead to some trust into these systems, but it also shows that we could invest more work to make them more trustworthy. Unfortunately, we also found that many of these classifiers use at least some bias. This is something we should keep an eye on and develop classifiers that ideally don't use any of these bias features, maybe by using debiasing techniques during training. Thank you very much.